Hello, welcome to Edexcel A2 Statistics in 30 minutes. My name is Tony Debling and I'm going to take you through some key revision points for your statistics exam. First of all, let's just take a look at what's in the formula booklet. At this stage, I'd like to highlight that there is a definition of SXX. Sometimes you're given a value for this and you'll need to refer to that formula. You're also given two formulations for standard deviation. You're not actually given the frequency table version, sigma fx squared over sigma f minus mu squared all square rooted. So you need to be aware of that one. And the others we'll refer to as we press on. Okay, let's start with correlation. Ornithologists trying to relate tail length to wing length. The objective of the ornithologist is to predict wing length from their tail length. It's important to know that you should only use a regression line to predict the response variable from the independent variable. This is because the recipe generates a different line if the variables are reversed. This indicates T will be the independent variable. So the tail length's independent, and we're going to predict the wing length, the response variable. Here's a picture. The regression line will always pass through the average of the t values and the average of the w values, and it will cut through the various plotted points. You're asked, what's extrapolation? Extrapolation is when the regression line is used to predict values outside of the range of values used to calculate the regression line. It's inherently risky as there isn't evidence that that trend will continue outside of the range. Prediction inside the range is called interpolation and it's statistically safe. Okay, so an ornithologist attempts to calculate the product moment correlation coefficient R and gets a value of 1.3. How do we know this isn't correct? Well, we know that a correlation coefficient will always be somewhere between -1 and +1. If it's -1, we have perfect negative correlation. If it's +1, we have perfect positive correlation. If it's 0 in the middle, we have no correlation. We're asked to use a calculator to calculate the correct value. I'm going to do this quickly with a Casio ClassWiz. So I go Shift Menu Option 6 to select the Statistics option. I choose option 2, y equals a plus bx, that's my regression line. Then I enter the pairs of values, x and y, x being the independent variable, y being the response variable, and I can use the arrow keys to enter the data. I choose option and then press 4, and I get the data that I require. So here it shows me that the correlation coefficient R is 0.7628. I'd also like to highlight that we have y equals a plus bx. B is the gradient of the regression line, and I can interpret that in the context of the question by saying that a rise in 1 millimeter in tail length will generally give rise to an increase of 0.6875 millimeters in the wingspan. Now we're asked, stating our hypothesis clearly at the 1% significant level, whether there is evidence that the product moment correlation coefficient of the population is positive. So is there evidence that these two variables are positively correlated? So our hypotheses are, the null hypothesis is rho equals 0. The alternate hypothesis is rho greater than 0. So we're going to use a one-tailed test. Were h1 rho not equal to 0, we'd use a two-tailed test. Now, to do this, we have to refer to page 37 of our formula booklet and look at the critical values for correlation coefficients. And to find the critical value in this case, we have to identify the sample size, which is 10. The significance level, 0.01, 1%, and that tells us that the critical value is 0.7155. So for our sample, the correlation coefficient is greater than the critical value, and therefore we can see that there's evidence that the variables are correlated. We reject the null hypothesis and accept the alternate hypothesis that rho is greater than 0. What does it suggest about female hook-billed kites? It means there's statistical evidence at the 1% level of significance that on average female hook-billed kites with longer tails will have longer wings. Okay. We also deal with exponential models with correlation. So sometimes it's clear a linear model is not the most appropriate if we're wanting to approximate all values in a range. So here they're curving. Sometimes these can be converted into linear ones by taking logs. Two cases. One, y equals ax to the n. We take logs of both sides, and we can see that there's a linear relationship between log y and log x. So we can use a regression analysis of big Y against big X, and then calculate the little a and little n. Similarly, case 2, y equals k b to the x, taking logs of both sides. We have a similar picture, but here we just take the log of y, we keep x as it is, and we have a linear relationship between big Y and big X. Okay. Moving on, we're going to look at some probability. A company has developed a test for a certain fault in the machine and its services, but the tests sometimes give incorrect results. So I've started with a tree diagram. Okay, these are faulty machines, these are non-faulty machines, and each case for a faulty and a non-faulty, it could test positive or test negative. So 2% of the machines have the fault. Of the machines with the fault, 70% test positive. Of the machines without the fault, 10% test positive. So I can fill in the 98% without the fault, and I can also calculate the two probabilities that a faulty machine tests positive and a non-faulty machine tests positive. So the next part of the problem is a machine is selected at random from the sample of machines and it tests positive for the fault. Calculate the probability that the machine has the fault. So this is a case of a conditional probability. Normally, we're asked to find the probability of a fault given that it tests positive. The word given's missing here, and we have to realise that it's conditional probability. For conditional probability, I prefer to look at a Venn diagram. So here, I have the set of faulty machines and those that test positive, and I can move the probabilities from my tree diagram into this picture. And now the probability that it's faulty, given that it tests positive, is going to be 0.14 over 0.014 plus 0.098, which works out as an eighth. And we have to comment on the usefulness. Well, it's not desperately useful, because this means that if a machine tests positive, it's still very unlikely that it has the fault. So it's not a very useful test. Okay, when the company services the machine, it checks two components, alpha and beta for wear and tear. And event A is that alpha needs replacing, event B is that beta needs replacing. So here I draw a Venn diagram. The probability of A, that's both these areas, is 0.35. Probability of B is 0.55. Probability that neither needs replacing is 0.28. Okay. From this recipe, I can work out that the probability that A or B needs replacing will be 1 minus 0.28, and this will be the probability of A plus the probability of B minus the probability of both. So I can calculate that the probability of A and B needing replacing is 0.18. And then I subtract that 0.18 from 0.35 to get the value 0.17. subtracted from 0.55 to get 0.37. Now my diagram is complete. So it says show that events A and B are not independent. If they were independent, then the probability of A and B would be the probability of A times the probability of B. And because 0.18 doesn't equal 0.35 times 0.55, this demonstrates that they're not statistically independent. By working out the probability that one or other but not both needs replacing, I simply add the 0.7 and the 0.37. And finally, I just want to make a note that, remember, mutually exclusive events are when they don't overlap. In this instance, we don't have any instances of mutually exclusive events. Okay, let's move on. The next question is about applying the standard normal distribution. It says a company has a customer services call center. It believes the mean time is 16, doesn't know the standard deviation. However, it knows that 10% of the calls take longer than 22 minutes. So what do? I draw a normal curve. So x here being the time it takes to complete a call. I know the mean is 16, and I write sigma for the standard deviation. I compare it to the standard normal distribution z with mean 0 and a standard deviation 1. The recipe or the formulation I prefer says that x is going to be sigma times z. When we multiply x by sigma, we spread out the values, and so we get a standard deviation of sigma. And then I add 16, I add the mean to shift it along to the position where x is. So next, I add in, I know 10% of the calls take longer than 22 minutes. So I want to find the value in the z distribution which corresponds to an area of 10 on the right hand side or an area of 0.9 on the left hand side of the line. So here I'm going to come back to my ClassWiz calculator. I'm going to go menu. I'm going to choose distributions, option 7. And now I'm going to choose the inverse normal distribution, which is key number 3. And I'm going to type in the probability 0.9, the standard deviation 1, and the mean 0. I type equals, and it tells me that the value should be 1.28155. So I'm going to put that value onto my standard deviation picture. Okay. I take these two values, the 22 and the 1.2816, and I can substitute them into the relationship between the random variables. I get this equation from which I can calculate that the standard deviation is 4.6818. Okay, now it says calculate the percentage of calls that take less than 30 minutes. 13 minutes, I apologise. So I draw on the line, it's before the mean. I draw this line here, and now I'm going to use my calculator again. I go to ClassWiz, I choose distributions, that's option 7. Now I'm going to choose the ordinary normal distribution, which is option 2. So I press 2. I fill in a lower value, which is 0, the upper value, which is 13, the standard deviation, 4.6818, and the mean, 16. I hit the equals key, and it tells me that the probability is 0.26051. So the probability that x is less than 13 will be 26.1%. Okay, we continue. It's quite a long question. In fact, most of the statistics questions are very wordy, so you have to go through them carefully. So here, a supervisor in the call centre claims that the mean is actually less than 16. He collects data on his own call times. And so 20% of his calls take more than 17 minutes. 10% take less than 8 minutes to complete. Okay? And it says, assuming this is a normal distribution, calculate the mean and standard deviation. So here again, we draw a picture here, but we don't know the mean. So we've got mu and sigma are both unknown. We compare it to the standard normal distribution z. And remember, x equals sigma z plus mu. The information we have. Okay, 17 calls take, 20% of the calls take more than 17 minutes. So I'm going to use my calculator. I'm going to use the inverse normal function. So I'll go to ClassWiz, option 7 for distributions. The inverse normal distribution is key 3. I fill in the probability. (0.1), and I find that the corresponding x value, z value, I apologise, is minus 1.2816. I do a similar thing for the right hand side. Again, choosing the inverse normal proportion, key 3. Here I put in 0.8. I want 0.2 after the line, so it's up to here. The probability is 0.8, sigma is 1 and mu is 0. I hit the equals key and I get 0.8416. So these two corresponding values I can plug into the relationship between the random variables. These two corresponding values I can also plug into the relationship between the variables. Two simultaneous equations in two unknowns. I can solve it to get sigma and mu. Okay, here we can see that mu is less than 16 minutes, and therefore that information supports the supervisor's view. Let's look at a more sophisticated question that they might ask you. Given that the call centre suggests it has a normal distribution with mean 16 and standard deviation 4.68. Here we're going to look at hypothesis test. The supervisor believes the mean is less than 16. She takes a sample of 16 calls and calculates the mean to be 4.2 minutes. Does this support her view at the 5% significance level? So here, mu is 16 is the null hypothesis. Mu is less than 16 is the alternate hypothesis, which suggests a one-tailed test. Now, the distribution of the mean of a sample of 16 taken from this sample will have the same mean of 16, but the standard deviation will be 4.6 divided by the square root of the sample size. You'll see that in the formula booklet. So in this instance, the standard deviation is going to be 1.15. We're going to look at the probability that x bar is less than or equal to 14.2. We're going to use ClassWiz again. Here, we're going to choose the ordinary normal distribution, so it's 2. We're going to put in a lower value of 0, an upper value of 14.2, a standard deviation of 1.15, a mean of 16. Press the equals. We can see that probability is 0.0588. This is bigger than 0.05, and therefore in this instance there's insufficient evidence at the 5% significance level to reject the null hypothesis that mu is 16. Close, but no cigar. Okay. You'll also need to be familiar with using the binomial distribution as well as the normal distribution and being able to distinguish when it's appropriate to use each. So recall the conditions for using a binomial distribution: a fixed number of trials, 2 outcomes for each trial, fixed probability of success, and each trial independent of the other. So let's take a look at this problem. We have a fast food company with a scratch card competition. It's requested that the scratch cards have a 45% chance of being a winning card. And what it's going to do is it's going to take a sample of 20 scratch cards from each of 8 fast food outlets, and it wants to work out that, assuming that 45% are winning cards, calculate the probability that in at least 2 of the 8 stores, 12 or more of the scratch cards are winning cards. So it's relatively complicated. So let's present our solution clearly. Let W be the number of winners in a sample of 20. So W will twiddle B20 0.45. So we can calculate the probability that there's 20 or more winners in these. That's going to be 1 minus the probability that W is less than or equal to 11. So we can calculate that on ClassWiz. Option 7 again. Here we actually have to go to the second page because we want the cumulative distribution for a binomial rather than the probability distribution. So we get the cumulative distribution, which is option 1. We choose 2 for a single variable. We enter the variable x as 11. N is 20, P is 45. We hit equals. We get the probability that W is less than or equal to 11. We press menu 1 to get back into ordinary calculation mode. Do 1 minus amps to get an answer of 0.1308. So that's the probability that there are 12 or more winners in a batch of 20. Okay. Next we let X be the number of stores with 12 or more winning cards. So here, X twiddles B, it's another binomial distribution. The number of trials is 8, and the probability of success in this instance is 0.1308. The probability that there are 12 or more winning cards in the batch of 20. So here we want the probability that X is greater than or equal to 2, which is 1 minus the probability that X is less than or equal to 1. Remember, this is a discrete variable, so we have to be very careful with greater than and equal to's. And we're going to do the same type of calculation. We're going to run through. We're going to go on to the second page to get our cumulative binomial distribution. Choose a single variable. Now X is 1, N is 8, and P is 0.1308. Equals, we get that probability that X is less than or equal to 1. We calculate 1 minus it as 0.2820. Okay. The next part of the problem is about approximating a binomial with a normal distribution. So it says write down 2 conditions under which the normal distribution may be used as an approximation to the binomial distribution. Okay. These conditions are straightforward. The probability of success in the binomial needs to be close to 0.5. This is to ensure we have a symmetric distribution, and there needs to be a large number of trials. So in this instance we have a random sample of 300 scratch cards, and we're going to assume 45% are winning cards, and we want to use a normal approximation to find the probability that at most 1, 2, 2 of these 300 cards are winning scratch cards. So we let W be the number of winners in a sample of 300. So W twiddles B 300 0.45. Here, the mean of this binomial distribution is NP. This is available in the formula booklet. We calculate it at 135. Sigma squared, the variance, is in the formula booklet. The variance is 74.25. So we square root this and we get a sigma of 8.6168. So we want a normal approximation to this binomial distribution. And the normal approximation, we'll choose something with the same mean and the same standard deviation. So the normal approximation x will twiddle n 135 8.6168 squared. So there's my normal approximation. Don't forget, when you use this normal approximation to calculate probabilities, you need to use a continuity correction. So the probability that W is less than or equal to 122 is actually equal to the probability, or approximately equal to the probability, that x is less than or equal to 122.5. We can calculate this. So go through class whiz. Option 7. We're going to go for the normal distribution, so it's option 2. Fill in the details, the lower, the upper. Sigma as 8.6168, the mean as 135, and we find out the probability equal to 0.0734. Okay. We have to comment whether there's sufficient evidence at the 5% significance level that the proportion of the company's scratch cards that are winning scratch cards are different from 45%. In this instance, what we're going to have is our null hypothesis will be that P is 0.45. The alternate hypothesis is P not equal to 0. We have to use a two-tailed test, and so here the probability of 0.025 in each tail, and so here it exceeds that. So there's not sufficient evidence at the 5% level to suggest the proportion is different from 45%. That's all, folks. I hope you found it useful. That's just over 27 minutes. Have a good day.